Statistics lesson 5.1, probability distribution. The objectives: define random variable and probability distribution. Determine when a potential probability distribution actually satisfies the necessary requirements. Given a probability distribution, compute the mean and standard deviation, then use those results to determine whether results are significantly low or significantly high. I went a little quick on that one, didn't it? Some terms. Random variable. A variable typically represented by x that has a single numerical value determined by chance for each outcome of a procedure. Probability distribution. A description that gives a probability for each value of the random variable. It is often expressed in the format of a table, formula, or graph. Discrete random variable has a collection of values that is finite or countable. Continuous random variable has infinitely many values, and the collection of values is not countable. Now, we've talked about these before, okay? We've made that distinction between discrete and continuous. Probability distribution. There is a numerical random variable x, and its number values are associated with corresponding probabilities. Number 2, the sum of p times x equals 1, where x assumes all possible values. Number 3, p of x is between 0 and 1 for every individual value of the random variable x. And let's take a little look at this. What if let's consider tossing two coins. This is our example. Let's consider tossing two coins with the following random variable. X is the number of heads when two coins are tossed. Let's make us a little tree diagram. Let's make us a little tree diagram so we can check these requirements here. I've already kind of put the answers, but the first coin, heads or tails, right? And the second coin, that's the first coin. And then the second coin is going to have the same options, but we had heads with the first one. So heads, and then say we got a tails with the second one. There would be heads and tails. And then tails or heads, and then tails or tails. If the first coin was tails and the second coin was tails, tails and heads and tails, heads and heads. Well, let's look at what we got. The above x variable is a random variable because each numerical value depends on chance. So there's a 1 in 4 chance or a 0.25 chance that we get heads. There's a 0.25 chance we get heads tails, a 0.25% chance we get tails heads, and a 0.25% chance that we get tails tails. Okay. Now let's break it down. So number of heads. All right, here we got 2 heads, right? And what's that percent chance? 1 out of 4, and that would be 0.25. These two here, we get 1 heads, but we've got 2 of them, so that would be 2 over 4, which is 0.50. And then this one here would be 0 heads, and there's 1 out of 4, and that's 0.25. 1 out of 4 chances. All right, so that's where I came up with this. That's where I came up with these. Okay, and they add up to 1. Each value of p of x is between 0 and 1, and you can see it. 1 out of 4, 2 out of, it's all, and when you add them up, 1.00. Okay, so that meets the requirements for a probability distribution. And to show you, here is a probability histogram over here, and here we have a table. Okay, now let's talk about this for a second. Notation for 0 plus. Sometimes you get something that is really small, like 0.0000001. Okay, if you rounded that, you would round it to 0. And if you said that there was a 0 chance, that means it's not going to happen. So what they did was they came up with 0 plus, okay, which means it is a really, really small chance of happening, but it could happen, okay? It can happen. So that's 0 plus. Example, hiring managers were asked to identify the biggest mistakes that job applicants make during an interview. The following table is based on responses. Does this table describe a probability distribution? What would you say? Well, let's see. The first one was there is a numerical value, not categorical, random variable x. Now, does this look like it is a numerical? It looks more categorical, doesn't it? So, number one, requirement number one. No. All right. What about requirement 2? The sum of p of x equals 1. Well, here the sum of p of x is 1.57. So requirement 2, no. And requirement 3, p of x, each p of x is between 0 and 1. And yes, that makes it. But since the other two are no, we would say no. Okay, this does not meet the requirement for a probability distribution. Parameters of a probability distribution. Remember that with a probability distribution, we have a description of a population. Instead of a sample. So the values of the mean, the standard deviation, and variance are parameters, not statistics. Statistics are for samples. Okay. The mean, mu, is the sum of x times p of x. The variance, sigma squared, let me write this right here. Mean, variance, sigma squared is the sum of x minus the mean squared times p of x, and the standard deviation is the square root of the variance, or the square root of the sum of x minus mu squared times p of x. All right. Expected value. A discrete random variable x is denoted by E, and it is the mean value of the outcomes. So the expected value equals the mean, and E can be found by evaluating the sum of x times p of x. All right, as an example of that, let's try. Let's consider tossing 2 coins with the following random variable. X equals the number of heads when 2 coins are tossed. We want to find the mean, the variance, and the standard deviation for the probability distribution. All right, so let's see here. Yeah, maybe we should make us a little table here. Let's do that. Let's make us a little table. And let's see here. We'll make us a little table. I don't know that we'll need that much, but we got it if we do. All right, let's see here. So we need x, and we need p of x, and we need x times p of x, and we need x minus mu squared times p of x. Okay, so we got this. Remember, we had 0, 1, and 2. So 0, 1, let's lose that one there. 1 and 2, and I'm going to put just on the bottom the total. So we got 0, 1, and 2. Okay, what's the probability of 0? 0.25. And the probability of 1 was 0.50, and the probability 0.25. So 0 times 0.25, 0 times 0.25 equals 0. 1 times 0.50, that's times, equals 0.5. And then 2 times 0.25 equals 0.5. So that equals 1. So we could say the sum of mu equals the sum of x times p of x equals 1. So this is our mean. Our mean is 1. So our mean is 1. Next, okay, so what do we got? We got 0 minus 1 here. We got 0 minus 1 squared times p of x. Well, that's going to be negative 1 squared times p of x. What do we got? 0.25 times 0.25 equals 0.25. And next we got 1 minus 1 squared times 0.50 equals 0. 1 minus 1 is 0. 0 squared is 0. 0 times 0.5 is 0. And then we have 2 minus 1 squared times 0.25 equals, well, 2 minus 1 squared is 1. That's going to give you 0.25. If we add these, that is 0.50. And this is sigma squared, which is the sum of x minus mu squared. I don't have enough room there. Maybe let me, I'm gonna make I'm gonna make it where you can see this. That's not what I want. Let's get the white out version. There we go. There we go. All right. So mu equals the sum of x times p of x, which equals 1, and sigma squared equals the sum and then you got x minus mu squared times p of x, and that equals 0.5. Okay, so sigma squared equals 0.5. You take the square root of that, square root of 1/2, that would be sigma equals the square root of sigma squared, which is 0.707. Okay, and for us, we'll just use 0.7 for this. Okay, so that's how you find them, and we will do more of these in class. Okay, but since we had that, we thought we'd kind of show a little bit. Range rule of thumb. Significantly low values are mu minus 2 standard deviations or lower. Significantly high values are mu plus 2 standard deviations or higher. Values not significant are between mu minus 2 sigma and mu plus 2 sigma. So those here in the middle are not significant. That's supposed to be like 95% of the data, isn't it? Within 2 standard deviations is 95% of the data. All right. So well, what about what we just did? Okay. What about what we just did? We found that tossing 2 coins, the mean, let's see, the mean was 1 and the standard deviation was 0.7, right? We'll use those results. So what do we got here? Mu plus, so that would be 1 plus 2 times 0.7. And that's going to equal 2.4. So 2.4, all right? And then over here, that's going to be 1 minus 2 times 0.7. And that's going to be, let's see here, what is that? That's 0.1 minus 1 minus 2 times 0.7. And that's negative 0.04, negative 0.4, all right, negative 0.4 is right there. So is getting 2 heads significantly high? Getting 2 heads, well, the probability of 2 heads was it was 1, wasn't it? Well, the mean number of heads was 1. The variance was 0.25, and the standard deviation was 0.1. So the expected value of number of heads of 2 tosses was 1 head. Of 2 tosses was 1 head. So I don't think it would be unlikely to get 2 heads, because 2 heads, that would be 2. This is 2.4. So getting 2 heads in this case would not be significantly high. Identifying significant results with probabilities. Significantly high number of successes. X successes among n trials is significantly high number of successes if the probability of X or more successes is 0.05 or less. That is, X is a significantly high number of successes if the probability of X or more is less than or equal to 0.5. Significantly low number of successes. X successes among n trials is significantly low number of successes if the probability of X or fewer successes is 0.05 or less. That is, X is significantly low number of successes if P of X or fewer is less than or equal to 0.5. And this goes back to here, okay? So we calculate all this stuff. What does it mean? Okay, are the values significant or are they not? And if they are significant, are they significantly high or are they significantly low? So I guess what I'm trying to say is the goal is not necessarily to calculate the value, it's more to interpret the results after you calculate the value. All right, which this leads to the rare event rule for inferential statistics. And that says, if under a given assumption, the probability of a particular outcome is very small and the outcome occurs significantly less than of the significantly greater or less than or significantly greater than what we expect with that assumption, we conclude that the assumption is probably not correct. Okay, not correct. So here's an example. Is 252 heads and 460 coin tosses significantly high number of heads? Well, how many would you expect? How many would you expect? Let's see. Well, is 252 heads and 460? Well, what's the probability? The probability of 252 heads out of 460 coin tosses would be 0.0224. Okay. Now we're going to learn how to calculate that in the next section. Okay. But is this significantly low or significant? Is this significantly high? Well, on the last slide, we said 0.05, and this is less than that. So we would say that this is significantly high. Okay. Well, what was the expected value? Well, the expected value was 1. Okay. So you were expected to get 1, but 2 at a 0.25% chance. All right. Well, we'll learn how to do that in the next section. Can't wait, right? Expected value in progress or in practice. You have $5 to place on a bet in the Golden Nugget Casino in Las Vegas. 2 choices. Roulette, you bet $5 on number 7 in roulette, or craps, you bet on the pass line in the dice game of craps. So what do you do? Well, you would probably try to calculate, well, if you were thinking about it. I mean, if you're just out for fun and stuff like that, you know, who knows which way you're going to go. But if you were out to make money, you would want to get the biggest bang for your buck. And that's where expected value comes into play. So what I've done here is the expected value in practice, the roulette, okay? The roulette, you lose $5, okay? Over here in craps, if you lose $5, okay? And probability of X, 37 out of 38, negative $4.87. 251 out of 495, so you supposedly lose negative $2.54. But if you win, and this is the net gain, okay, that's minus the $180, minus the $5 that you put in would be $175. The probability of X of 1 over 38, you would make $4.61 for a total of, for a total of a loss of 26 cents. Okay. I wonder how them casinos are staying in business. Craps, win, you would win $5. Okay. Minus the $5, well, $10 minus the $5 would give you a total of $5. 244 out of 495. That would be a gain of $2.46, which is a net loss of 0.07. And that's this minus this equals A minus B equals C right here. Okay. So, stand to win big, you're going to lose more. Stand to lose or win little, lose little. Okay. And that's kind of the way those casinos work. Okay. Great job, folks. See you tomorrow in class. Have an awesome evening.